So I'm going to leave that for now. We're going to leave powder metallurgy, and we're going to move into welding and joining. Really almost a complete opposite type of process. Whereas the powder metallurgy we were talking about is a solid state process that uses powders to make components. Welding is widely used across all aspects of materials fabrication and metals fabrication in particular. It's our way of joining things. As I had mentioned in the introduction to the lesson, if you can't weld it, you can't build it. It's almost as simple as that. And so you need to be able to form a metallurgical bond between two or more metal parts. And typically that's done by melting the two work pieces. You melt a little bit of each work piece, you add a filler metal, you form a molten pool, it creates a strong joint. Soldering and brazing are different. What they tend to do is they add a third element in there. So you would have a joint between two materials, and you add a third material in there. And that third material tends to be lower melting point. And that is melted, and it wets to the joint, and it wets across the joint. So the other two are the two materials that you're actually joining together never melt. That's the difference in soldering and brazing. So soldering is low temperature, brazing is high temperature. And so in welding, we don't always need to melt. That's where the difference between fusion and solid state welding go. And so what we're going to do is we're going to run through a bunch of fusion welding processes, give you some idea of the range of different materials that are there. But before we do that, we're going to concentrate a little more on fusion welds. And this image in and of itself is pretty important. I would definitely understand the different regions of a fusion weld that occur. So if you think about it, I am melting material and I'm joining two parts together. About everything we've talked about in the course up till this point occurs within really almost several millimeters or maybe an inch or two. Everything. Solidification, we have melting, we have solidification, we have solid state transformations, we have mixing of materials. Everything that happens in steel mill, anything with metals processing on larger scales happens in a very short time frame, and it happens very quickly in welding. That's what makes welding so interesting. And so within there are certain regions that I want you to really take into account. First one are the two work pieces, and we have a joint. And what we're showing here is, for the most part, what we consider a butt joint. We just take two flat surfaces and place them together. But as we add weld metal, or if we do something that's called autogenous welding, is we just melt the two work pieces together, we create a fusion zone. And so the fusion zone is what has been melted and where the filler metal may be added. So we have this weld metal in this fusion zone. The second one is we have what is fused base metal. So we've gone below. We've actually melted some of the base metal together. And so we can call it a fused base metal. I like to call this a dilution zone. And then next to that, we still have pretty high temperatures because we're melting metal up here. And so with that, we create solid state phase transformations because of the high temperatures that each of the two work pieces have seen. This is called a heat affected zone. No melting generally in a heat affected zone. So that's important. This is solid state process. In a lot of cases, welds don't break in the weld metal. Welds break or failure occurs within this heat affected zone. And so this is where you really want to concentrate. If you start seeing defects in welds, and believe me, the first thing that's going to fail in any component is some type of joint or interface, and welds are primary drivers for failure in a material. And so if there's a failure occurs in a structure you're looking at, usually from a time perspective, usually the first place that you want to look is in the fusion zone. And so to give you some idea of some of the microstructural changes, these are images that came out of my lab. These came out of a work that I had done several years ago in a 1045 steel. If you remember, 1045 steel has 0.45 weight percent carbon. And so this is over a couple millimeters from a fusion weld. So the fusion weld was located over here, and this is a microstructures that we saw. So what you tend to see here is within that fusion zone, we are seeing from the base metal to different transformation regions of how complex these heat affected zones can get over very small areas. So you see a significant change in the microstructure just over such a small range of materials. So what we have is these fusion welds. So the question becomes, okay, so we have different work pieces. We're melting a little bit of them. We're creating these heat affected zones. And we're creating this weld metal. Now, in a lot of cases, the only thing I can do to minimize failures in the heat affected zone is to decrease the amount of heat that I put in. But when I choose weld metal, I don't want the weld metal to fail first. So this is where the idea of weldability comes. And so weldability is a general catch-all term. Even within the welding research community, you will ask somebody what weldability means, and you will probably get different answers from. If you ask 5 people, you'll get 5 different answers. It's a fairly vague term, but it refers, for the most part, to the ability of material to be welded. And so the important factor, which welding process you're going to use, which materials you're going to select, what your filler metal or your weld metal is going to be. Because in most cases, weld filler metals have slightly different compositions than the base metals that they're welding. And so if we talk about steels, what we really want to talk about in weldability of steels is determined primarily through something called equivalent carbon content. And what we see here is an equation below. And so it's used to compare the relative weldabilities of steels. And we want to compare them, for the most part, to plain carbon steels. And so high strength, low alloy steels, and we see these different alloying elements here, whether it's manganese, silicon, chromium, molybdenum, vanadium, copper, nickel. We make all these additions to these steels. So weldability, when we say it's inversely proportional to hardenability, we know what hardenability is. Hardenability is the ability to form martensite, which is brittle. It's strong but brittle. And so in most welds, we want to make them tough. And so that brittle nature of that is something that we sometimes want to avoid. So you don't see a lot of martensite per se, or attempts to really maximize the amount of martensite in a weld metal. What you're trying to do is avoid that and keep the weld metal from cracking, because as I mentioned, if you really think about something that heats and cools rapidly, we're creating a lot of residual stress within there, especially through the solidification process and then through the rapid cooling that will occur. So hardenability, we know, depends on composition. So what we want to do is, if we have higher hardenability, we tend to have lower weldability. And so what we want to try to do is to minimize this carbon equivalent. Lower the carbon equivalent, the higher the weldability and the more weldable that steel alloy is. And so remember that. So you may be asked on the exam that's coming up of what type of carbon equivalent. If I have 2 steels, which one is more weldable? The one with the lower carbon equivalent is going to be more weldable. Now, these are just with plain carbon steels for the most part, or or low alloy steels. Stainless steels tend to be weldable. They tend to behave differently, though, with respect to weldability. The austenitic grades, if we remember, those are the ones that have primarily an austenite structure to them, the 300 series stainless steels. They tend to be the most weldable, but they're susceptible to some distortion. They are prone to cracking in some cases, and you do see reduced corrosion resistance. And that went back to, if you remember, intragranular corrosion or sensitization of stainless steels back in the corrosion lectures. Hot cracking is another issue. Other ones aren't quite as easily welded. So the weldability of stainless steels, there are certain research groups that have spent a lot of time looking at weldability of stainlesses and of austenitics and trying to understand what creates cracking and what doesn't. But that's for a more in-depth course on weldability. For the most part, most stainless steels, you need to pay attention to how you process them to make them weldable. Aluminum tends to be a little more difficult. They're susceptible to what they call hot cracking, and that has to do with those alloying elements that segregate into interdendritic regions. You can increase speed, lower the heat input. Preheating is one to decrease those cooling rates across there. You can change the joint design. You really worry about cleaning up joints and doing that, but in a lot of cases what it comes down to is the selection of a filler metal that is weldable, or it's almost a eutectic. And aluminum and silicon form a eutectic at about 12% silicon. You're going to find a lot of welding filler metals use that type of composition in order to make the aluminum more weldable. Now, So we've seen sort of the weldability. We've seen the different microstructures of a fusion zone. There's some different joint geometries. I just want to bring these up because people will tend to use these. And if you go to work in a fabrication house, you're just going to be expected to know what they're talking about. So butt joints can either be straight butt joints across the thickness of the material, or you can add a V. They're still butted together with each other. A lap joint overlays one over the other. T-joint, or is called a fillet, not a fillet, it's a fillet. And so it basically forms a T-joint, and the welds are going to be made at the corner, so you're making a wall for the most part. And so you have different welding processes that use these different joint types. And so we're going to quickly go through these. Just important that you know that they're there. The vast majority of them use arcs as their primary energy source. And the first one we're going to talk about, this has been called TIG welding, TIG welding in the older nomenclature. The current nomenclature that American Welding Society and a lot of the standards associations use is gas tungsten arc welding. And in this case, you feed your filler metal rod through a separate action. So it can be manually fed or automatically fed into that. Your primary energy source is a tungsten electrode, gas tungsten arc welding. You can also weld autogenously in this process, and it's used for stainless steel, aluminum, magnesium, copper. It's a widely used process. It's a very high quality welding process, as you can imagine, with the tungsten electrode. Shielded metal arc, this is what you would call stick welding. And usually the first way that people learn how to weld is by using this stick weld. And you'll see it if you drive across where they're doing welding on a bridge or some other places, you'll see them there with a fairly long, what you would call a stick, or this flux or this rod with an electrical connection to it. Now, there's no shielding gas in this. In the gas tungsten arc welding, we feed inert gases around the weld metal to keep them from oxidizing. Typically argon or some combination of argon, helium sometimes, depending on the level of heat transfer that you want in the weld. The shielded metal arcs use what is called almost a flux on the outside of it. And what this does is creates a slag. So it uses chemistry from the melting of the metal to produce a protective layer. So usually when you're done welding with a stick weld, you end up with a slag on top, which you can remove with a wire brush or some other type of little implement, either grind it off or just knock it off. And so this slag provides the protection from oxidizing of the weld metal deposit. Gas metal arc welding is probably really where, if you're going to be commonly used, this is what is commonly used. And instead of a tungsten electrode, the filler metal wire itself is the electrode. And so it's directly melted into the joint. And it can be melted in a number of ways. And usually how it's melted depends on the type of arc or the current and the voltage that is used to melt that material. And it can be melted in such a way, and because of the high amperage or the high voltage that is used, it can transfer in a number of ways. So it can transfer as a globular. Short circuit means you just have the metal wire will actually touch or be buried in the weld pool. That's what short circuiting means. Spray it comes off as small beads. It's almost like a spray of an aerosol process. It's the most common one that you see. And for filler metal, companies like Lincoln Electric, ESAB Brothers, Arcos, different companies that you may run into that sell filler metal, this is their bread and butter, what they sell for. A related process is flux core arc welding. And so in traditional gas metal arc welding, you use an argon shielding gas to be able to protect the environment from any oxidation or contamination from the environment around it. Flux core, there's no shielding gas. The flux, much like what we saw in the shielded metal arc, is within. So the metal wire itself is actually hollow, and the flux is placed in there. So you will have to, after you're done, knock off some of the slag that may be there, but you don't need that a shielding gas attached to the torch, which is always beneficial. But as we saw from our bridge failure, that is the type of process that resulted in some weld cracking if you don't control what the chemistry of that flux is. Submerged arc welding is, just as the name sounds, it's a continuously fed process. There's no shielding here because they literally cover the electrodes. So the electrode is buried in what's called a flux, which is that slag. It creates that slag. And now submerged arc welding is typically used for really deep penetration welds. It's a very high efficiency process per se, where you feed a rather thick electrode wire. Current is run through that wire and it's buried in this arc. So you don't even need a welding shield or anything to produce this process because you just see no flux. It's really the only thing you really feel in this type of process is the heat. And it's unique in that the flux is reused. And so there's literally, when you see submerged arc welding, you'll see almost a vacuum cleaner behind it that is picking up the flux as the weld is made, or as the weld cools after a certain period of time. And so another one that's commonly used is resistance welding. So each of these used arcs as their torch or some type of electricity. Resistance welding uses electricity as well, but what it does is it heats up the part by resistively heating it. And they're efficient. They don't have a lot of pollution, but they are rather small. And so let's see an example of where we can see resistance welding in action.
Very high electric currents are used to quickly produce the resistance heat necessary for fusion. The three principal types of resistance welding are spot welding, seam welding, and projection welding. Spot welding refers to making welds one at a time between the electrodes. One, several, or many individual spot welds may be required, depending on the application. Spot welding, with the electrodes maneuvered by articulated arm robots, is commonly used to join sheet components of automobiles. In seam welding, coordinated pulses of electric current from rotating wheel electrodes produce a series of overlapping spot welds, resulting in a lead-type welded joint. In projection welding, the welds are localized at predetermined points by projections, embossments, or intersections. Several points may be welded simultaneously.
So in there you see how the electrical current flows through and creates these resistance welds. So you would see in the automotive industry particularly, most of the vehicles that have been driven for years have been resistance spot welded together as their primary joining process. As we're starting to move forward in the automotive industry, lasers are becoming more. It's a little more versatile, and so I'll give you an idea of what a laser weld may look like. Is you're using a laser as a heat source, and what we're seeing there is shielding gas, and then what this is an exhaust that's basically consuming all the fumes that come out of that. And so what you see in a laser welding process is a process that is much, much more rapid. This is done on an older CO2 system in a lab here at Penn State just to demonstrate welding of this component. And so in laser welding, you typically, the wire would have to be, any filler metal that would be used would have to be added, much like in a gas tungsten arc welding. But laser welding is unique because laser welding produces not just what we consider a hemispherical shape, but the laser has such a high energy density that creates a vapor cavity, and so it creates a keyhole. So what you create in them is a vapor cavity down in the middle of the weld, and what it provides us is deep penetration, low distortion, and very small welds, and so very small heat affected zones as well. So they tend to be very good for that type of process. Now, electron beam welding is a related process. Instead of a laser, it uses an electron beam. These tend to be operating in a vacuum as well. So the electrons tend to create the melting process, and it's very similar, but in a lot of cases you produce much deeper welds. So the sort of what we consider the aspect ratio, or this width or depth to width ratio that we may be looking at, is much different than other welds. And so you can produce very thin welds that are very deep in nature. Now, these are sort of the range of the different fusion welding process. So we can use arcs, we can use electricity, we can use lasers, electron beams.